Okay. So real quick, I'm kind of tired for this video, so if you notice I made a mistake, or if I notice I make a mistake, I'll fix it up in the next videos, because this is gonna have to be multiple parts. It's a very big function. So this is the function which initializes and inserts the APC into threads. Now, we start off with very simple. We just access some sort of a structure, which this seems like it contains so structure plus 0x130 and then 8 times 76. So it seems we're accessing, I believe, an array in that structure, and we are checking if that thread is equal to pskit current thread ID. So I'm guessing we're checking if the kernel thread we're scanning is equal to the current Battleye thread, kernel thread. If it is, we don't do any of this, right? So we're assuming it's not. We do ps lookup thread by thread ID, sort of MP thread. We allocate a pool. We initialize the event in v9 plus 0x7 0x58. We initialize our APC on that thread, on the thread that we're currently scanning. With this, that goes to this. So with this callback routine, then we insert it. Now, and we do ke wait for single object, which is triggered by this ke set event later. Now, if you don't know what RTL walk frame chain does, is it essentially takes a thread address as a argument. It walks that thread's I forget what the structure is called. I think it's like a runtime function structure, which contains unwind info. So it basically uses the basically just walks that thread's stack to get return addresses. So this just returns return addresses. The actual return value is a number of frames, right? Keep this in mind. Plus what does that say? 870. And it's storing the return addresses in A4 plus 0x70. So this it's storing it. This is our system argument, which it's modifying here. It's dereferencing and modifying, right? So anyways, we go down, we call this function, if not this. We go down, we do this, wait for a single object, then we leave. We're assuming that doesn't happen. And we're just gonna go to the cool stuff. So number of frames is equal to system argument plus 870. Remember I told you that's where it's stored. That's the number of total return addresses there are in that thread. We initialize a counter, v80, if the number of frames is greater than 1. We go down, we access APC plus, remember I said the return address is stored in 0x plus 70. We access our APC structure. They use structures to represent this. This is from Battleye strictly. So we go APC plus 0x70. We access the frame array. We choose a frame, a specific frame. I already reversed this. This global variable points to some Battleye structure where plus 18 contains its Battleye driver's base address and plus 20 contains its size. So we go down, we get the return address. We check if the return address is less than Battleye kernel driver's base address, or if it's greater than Battleye kernel driver's base address, which means it's not in Battleye. So if the thread we're examining, the kernel thread we're examining, oh, by the way, the reason I know we're examining kernel threads is because it's checking if the highest bit is set here. This is filtering for kernel addresses, right? So this whole logic is for kernel addresses. Kernel threads, sorry, I should say. Specifically kernel threads. Anyways, if the kernel thread frame we're walking the frame chain on, the return address is not in Battleye. I already reversed this too. This global list is a kernel mode struct list. Pretty straightforward. It just contains kernel mode modules that are in memory at the time. If it's not, we break. If it is, if it exists, we go here. We get our kernel module base plus 508. I already reversed this, so that's how I know this is kernel module base, and how I know this is kernel module base size. Um, if the return address is over the kernel module base, if it's less than the kernel module base plus size, so if it is actually if the module which the thread belongs to is found, we break out of this do loop, we go to this while loop. Kernel module, this is actually set. Yeah, wait. Yeah, so this would actually be set. And we would increment and we would move on to the next frame in our thread stack, and we would verify that one, right? And it does this for the number of frames that there are. So anyways, um, let's see. Yeah. So let's say a malicious return address is found where that return address does not belong to any valid module. This loop will finish, this do loop will finish. We will go down. This will not be set. Kernel module list struct will not be set because it will go to the end of the list and it will be set to some junk value, right? Or it will never be set, right? So we go down, we just break out of the while loop now. We go here, and there's a bunch of cool shit here. That's why I'm gonna do a second part to this video, because if a malicious thread is found, or a malicious thread, I should say return address is found from RTL walk frame chain, then we do some cool stuff here. Like down here, I noticed they're walking the stack and they're looking for jump addresses, and then they're calling is address valid on that jump instruction right here. So it's pretty cool stuff. They're doing their own version of stack walking on kernel threads. It's not really stack walking. There are some limitations to how they implement it, like how far they reach, or yeah.